To evaluate limits algebraically, we have to develop some limit laws, and we start with the basic limit results. We're going to look at two simple functions. One of them is the function f of x is equal to x, and the other one is the function f of x is equal to 2. And 2 is not very special here. We're really just talking about a function that's equal to a constant, and it could be any constant. Positive numbers, negative numbers, large numbers, small numbers, decimal, you get it. These two facts will help us build the rest of our limit laws. So if we wanted to talk about a limit regarding the function f of x is equal to x, the first thing that we need to recognize is that every point on this function is going to have matching x and y values. A limit for this type of function basically says when x is heading somewhere, y is going to the same place, or our function behavior is matching that input behavior. So for any limit where x is approaching a number like a, for the function f of x, that limiting value is going to be equal to a. Wherever x goes, y goes. What about for a constant? If we were to pick a few points for this function f of x equals 2, notice that the x value might change, but the y value is the same for every point on this function. So remember that limits report the output function behavior, not the input necessarily. So here, x is allowed to travel towards a, but notice that the function output is consistently 2, so the limiting value for this function, where f of x is equal to 2, is equal to 2. We can use these two basic limit results to evaluate some of the more simple limits. For example, if we're talking about the limit when x approaches 2 of x, we know that where x goes, y goes for that limit. If we're talking about the limit where x is approaching 2 for a constant, 5, we know that the constant is constantly constant. It's not changing, so that limit is equal to 5, the constant that we were talking about. What about the next one? Again, we're looking at the limit for a function x. X is heading to -1, so that limiting value is also going to -1. Our next one is the limit of a constant. This constant is the fraction 2/3. We don't really care where x is heading, but if we did want to talk about x heading towards 2, we would say the limit of this constant is equal to 2/3. The next one, the limit of x when x is approaching 0. Well, if x is turning into 0, then the limit of x is also 0. One more, we have the limit of a constant. The constant is -1. We don't really care where x is heading, but it is heading towards 2. So as x approaches 2, the limit of -1 is, oopsies, +1. That should not say 1, it should say -1. Now we can build upon our limit laws. So we're going to generalize this for a couple of functions. We have f of x. We know the limit of f of x when x approaches a. We don't know anything else about f. I don't know what f is equal to, so I cannot do a substitution where I replace f with its definition. I can only do substitutions where I see the entire notation, the limit where x approaches a, for the function f of x. I can replace that limit notation with what it's equal to. In this case, it's equal to m. Same thing for the g of x function. We don't know the definition of it. We just know that as x is approaching a, the limit for that function is equal to a limiting value n. We can use this fact to show how to evaluate limits when we have a sum, a difference, or a constant multiple of a function. Let's take a look. If we wanted to take a limit of two functions being added together, we could instead separate the two functions and apply the limit to each function first, then add them together. So the limit goes into this sum and applies to each of the functions that are being added together. And since we know that the limit when x approaches a of f of x is m, and the limit as x approaches a of g of x is n, we can just say that that sum is the same thing as m plus n. Now if we had, instead of f plus g, if we wanted to talk about f minus g, how different would that look? It's almost the exact same thing. The difference is that we have subtraction between the two functions. So the limit operator is allowed to be distributed over this difference so that we have the limit of f minus the limit of g, which we know would look like m minus n. What about a constant multiple? Now in this case, I'm using the letter k to represent a constant, and I promise you, although I'm terrible at spelling, I do know that constant is spelled with a C. The problem though is that we've used C in other things already, and so we want to distinguish the fact that we're talking about a constant multiplied to a function, not a constant all by itself. In this case, k is some number, like 2, and it's being multiplied by a function f. If we wanted to evaluate this limit with the limited information that we have, we would first need to pull the k outside of the limit operator. This means we can substitute in m for the limit of f and say that this is equal to that constant times m. Now one thing I really want to point out here is that I'm not immediately replacing f with m, and that's because f of x is not equal to m. The limit of f of x is equal to m. So I first have to separate the limit and apply it to each of the terms that I'm adding or subtracting together. And then I can do the substitution, where I pull out the entire limit of f and replace it with m. We have two other rules to look at, product and quotient. If I wanted to take the limit of a product, I could distribute this limit operator to each of the factors in my product. So my factors in this case are the functions f and g. I can apply the limit to each factor, so the limit of f multiplied to the limit of g. And now that I have those limits and their functions written out explicitly, I can do my substitution. I can pull out the limit of f and replace it with m, pull out the limit of g and replace it with n. So now I can see that the limit of a product is the product of the limits. For a quotient, we have to be careful that the bottom function is not equal to 0, that we're not creating an undefined situation. And as long as that's the case, we can apply the limit law where we put the limit into the numerator and the denominator separately. And now, again, since I have the limit of f isolated, the limit of g isolated, I can do a substitution where I have m over n. The limit of a quotient is the quotient of the limits. We have two more rules here to look at. That's the power rule and the root rule. The power rule says that if I'm looking at the limit of a function which is being raised to an exponent, I can sneak the limit operator inside of that exponent, and now that I have the limit of f isolated, I can do this replacement where I pull out the limit of f and replace it with m, the limiting value. So the limit of f raised to the power of n is the same thing as taking the limit of f, which is equal to m, and then raising it to the power of n. Roots work the same way. Remember that all roots, all radicals, can be rewritten as rational exponents. So if we were allowed to sneak a limit operator inside of an exponent, then we should be allowed to sneak a limit operator into a radical. And once we have the limit of f isolated, we can do this direct substitution where now we see it's the limit of m, that limiting value. So in short, these are all of our limit laws. We have a sum, difference, constant multiple, product, quotient, power, and root law. And I'm going to consolidate the sum and the difference laws because they're so similar. The only difference is the plus and the minus, just to simplify our notation here. Let's practice using these limit laws to evaluate some of our limits algebraically. We're not using graphs, we're not using tables, We're getting straight to the point. Each step, we're going to identify what law we're applying, and then we'll apply it and move on to the next step. Here we're looking at the limit where x is approaching -3, and the function that we're investigating is 4x plus 2. The first thing I notice is that we're adding two terms together, so we're applying the sum limit law. That means we're going to separate the terms and apply the limit to each term separately. Next, I notice that in that 4x term, I have a constant multiplying to my x, my function of x. I'm going to pull that constant outside of the limit operator, and then I recognize that I'm just looking at one of my basic limit results, the limit of the function x when x is allowed to approach -3. This is the limit where the limit goes wherever x goes, so that limit is equal to -3. But I will be multiplying it by 4, so it's not finished yet. Let's look at the other limit in our notation. This is the limit of a constant. That's one of our basic limit results. The limit of the constant 2 doesn't even care where x is going, although it is heading towards -3. That limit's equal to the constant 2. So now I can copy everything down and consolidate. I have 4 times -3 plus +2, and this is equal to 10. That is the value of this limit evaluated algebraically. Let's try another one. Here we have a rational function, 2x squared minus 3x plus 1, all divided by x cubed plus 4, and we're allowing the limit of x to approach 2. The first thing I notice is that we're dealing with a quotient. I have a numerator, I have a denominator, therefore I'm dealing with a quotient. We apply the quotient rule as long as the denominator will not be equal to 0 when we evaluate our limit at the bottom. We separate our limit into the numerator and another limit into the denominator, and we're ready for our next step. I recognize in my numerator I have 3 terms. We have a difference and a sum, and in the denominator we have 2 terms. We have a sum. So we need to apply the sum and different limit laws, separating our terms and applying the limit to each term. Next, I recognize that we have some constant multiples. We have 2 times x squared and 3 times x. Let's go ahead and pull those constants out of the limit operator and move on to our next step. Next, I recognize that we have some powers on our variables, and our power law says that we can sneak the limit inside of that exponent. So rather than the limit of x squared, we're going to square the limit of x. And rather than the limit of x cubed, we're going to cube the limit of x. And now all of the limits we have on the screen are the same as those basic limit results that we saw at the beginning of this lecture. So we can do our evaluation. The limit of x when x approaches 2 is 2, and the limit of a constant is equal to the constant. So we'll replace each of our limits with their values and consolidate and simplify. We get 3/12, which reduces to 1/4. So this limit is equal to 1/4, and we used our limit laws to step by step get to that result.